Hello and welcome back to my channel. In this video we're talking about how to use LP to model maximum independent sets. We had discussed the maximum independent set problems in a few videos before now. Maybe you can go up to look at it if it's something you are very new to. So this video is going to be kind of very short because it's going to be a contrast of the last video where we talked about using LP to model vertex cover. Now, for the vertex cover, we wanted to select a minimum size subset of vertices that covers all edges. And like I said, that was a case of at least, just in case you missed that video, just, a recap. If we wanted a minimum size set of vertices that covers all edges, that means for, let's say you have edge UV, we don't want a case where nothing covers, right? We don't want this. So we want either this, or we want either this, or we want either this. So this is the at least case, right? And that's why in the formulation, the constraint formulation, we have greater than or equals 1. So now in this maximum independent set, we want a maximum. In this case, we want a maximum subset of our vertices such that for each edge, at most one of U and V is an I. So in this case, we want a maximum. So let's translate this to an LP problem right away. So this is the LP translation. First of all, our variables. Just like in the vertex cover case, we're going to use XV, where this is the vertex, right? We use this to represent a vertex. And our objective function here, just as you have seen in this definition, is to maximize. So we want to find the max xv1 plus xv2 plus to xvn. And then we define our constraint. So first of all, our constraint would be that we either choose a vertex or we don't. So that means a vertex is either 0 or 1 for all v's in vertex, right? And this means that xu plus xv would now be less than or equals 1. Remember, this is an at most case. At most one of U and I is an I. So this is an at most case. I really want you to be able to remember this pointer, because when you have a random question, if you can tell the difference between an at least question and an at most question, it helps you formulate your constraints very easily. So in this case, we want at most one of U and V to be in this subset of vertices. So this is an at most question, which is less than or equals 1, expressed as less than or equals 1. So this is the second constraint. And if you notice, this problem is also a 0-1 LP problem. It's also a 0-1 LP problem. And this means that it's going to be a hard problem and we need to relax it. We need to go through LP relaxation. I'm going to end this video here. In the next video, we'll pick up a couple more different scenarios that would model using LP, and I'd like to see you on the next one. If you haven't subscribed, please do subscribe. See you on the next one.